going to take the next 2 lectures to talk about the nervous system. So it's a big deal. So the nervous system pretty much works on charges. It works on ions. It depends on charges, and because it depends on charges, we say it uses electricity to conduct its signals, its messages. And so to understand electricity and neurons a bit, you have to kind of understand the basics of ions. So there's 2 types of ions generally. You have cations, those are the positively charged ions, and then you have the anions, a negative ion. And if you ever forget that, an anion is a negative ion. That's one way of thinking about it. Had a hard time thinking about it. And what do opposites do? Attract. Supposedly in love, like in love, they attract, right? That's actually kind of false as a rumor myth. Yeah, opposites don't necessarily attract in romantic affairs. So, positive cations are attracted to negative ions. That's just kind of how it is. And there's a chemistry explanation for that, but we don't care about that in this class. And so you can have situations where there is something in the way, right? These ions want to come together, but there's something blocking their path. There's something that's blocking their path, whatever it is. We can call this an insulator. Sorry, I have some random stuff on my screen. Yeah, this is called the insulator. It prevents charged ions to pass it. What's the opposite of an insulator? Yeah, conductor. So, go back. So you can kind of think, if this was all water, right? This water is like a conductor, right? Because it's allowing these ions to travel through it. It's allowing these charges to travel through it. That's a conductor. So another example of conductor is copper, right? That's what you find in your wires. If your fancy wire, sometimes it's gold, but those metals are considered conductors because they allow charge to pass through it, just like water allows charges to pass through it. But sometimes you have insulators. And an example of an insulator is, well, the cell membrane. Cell membrane is like an insulator, right? It keeps charges from one side of it separate from the charges on the other side of it. So this is the example of an insulator. And that's pretty much the name of the game for the nervous system. As far as creating electricity, it's keeping charges on the other side and occasionally letting one side through. And so you can have, because you have separation charges, you can have a charge difference, right? Here we can count it up. We have, 1, 2, 3 positive charges, 1 negative charge. We can say like a net charge of +2 here, right? And we have 1, 2, 3, 4, 5, 6, 7 negative charges. And then we have, what do we have here? We have 1, 2 positive charges. We have a net of -5, right? And so you can look at the charge difference here. And the charge difference here is, we will say, -7, because we can say -5 minus your +2 is -7, right? You say, well, Dr. Nair, why can't I do it the other way? Like, well, you could say 2 minus -5 is +7, and that's the same difference. But in the attempts to not confuse people, we pick one method over the other. And so generally, if this is inside the cell, the ICF, and this is outside the cell, we'll say this, that the charge difference, sometimes we call this the voltage difference. The voltage difference of a cell is the inside charge, the inside voltage, subtracted from the outside charge. The inside is the reference here. And in general, just like in this example, the cell's negative. It's about -70 millivolts. So that's kind of what's happening in our cells. We have this, what we call this disequilibrium of charge, where there's some charge inside the cell, there's some charge outside the cell, and they're in disequilibrium. That means there's disproportional amounts of concentrations on either side, right? Remember that from when we talked about disequilibriums. There's a disequilibrium of charge in cells, and that creates a charge difference, which we can word as a voltage difference. Now, we're not going to get into the physics of what charge is and what voltage difference is. You can just kind of think of them as synonymous, right? And so these are the different ions you typically expect to see in the body. We have cations, we have your good old sodium, potassium. There's a little bit of calcium in the mix too. These ones are the big ones we'll be concentrating on in the nervous system. Calcium's a little bit more important for muscles and some other, and as signaling molecules as second messengers in signal transduction. But we're talking about ions and electricity. Calcium is more of a signal and less of a ion thing for electricity. Then we have some ions. We have your chloride, and a big one for inside the cell are proteins. There's a lot of negative proteins out there, and you generally find them more on the inside of a cell than on the outside of the cell. And so these are the players here. These are the ones that are in chemical disequilibrium. And so here is our electrochemical system here. Here we have a lot of potassium, and we have a lot of these large anions, which we can just consider proteins. Those are inside our system. Now, keep in mind, I'm not calling this a cell yet. This is not a living cell. This is our artificial cell. This is just our just our spherical membrane with some charges on the inside and some charges outside. This is not a real cell. This is not what happens in a real cell. This is our kind of make-believe artificial situation. So in our make-believe artificial situation, we have potassium ions in the inside. We have negative ions, proteins, and then we have our sodium and our chloride outside. We basically have salt on the outside. This is generally what it appears to be like in the cell. Now keep in mind, if you just look at this system, if you add up all the charges together, it's zero. Like each of these can match up, each of these can match up, and so generally the system is neutral in charge, right? And that makes sense, right? You don't see people colliding together due to electrical discharge, right? I'm not flying to you because I'm positively charged and you're negatively charged. That doesn't happen, right? You don't see that kind of thing happening. You don't see people stuck onto like metallic structures because they're charged and whatnot. It doesn't happen. And because we're pretty much neutrally charged, and if you look at all the ions added up together, but there's still a disequilibrium here. Generally, on a given cell, there's more negative charges. There's more negative charge than there is on the outside. And we'll explain why in a bit. But in this artificial situation, let's say we made a leak. And in this leak, it's permeable only to potassium. Potassium can leave the system, but not these negative ions. These negative ions, these proteins, have to stay inside. That's just the nature of this leak. So what will happen is, well, let me ask you, what's going to happen when you make a leak for only potassium ions? What's going to happen? It's in the picture. Potassium is going to leave. All these guys, they're going to start leaving. Why do they start leaving?
Chemical gradient.
We're going down the chemical gradient. They're following diffusion, second law of thermodynamics, and they're going to go down the chemical gradient, which is high on the inside, low on the outside, so they're going to go outside, right? But when you start doing that, there's suddenly going to be more positive charge on the outside and more negative charge on the inside. What happens to positive charges and negative charges? They attract each other, right? So, as potassium starts leaving, they're going to be drawn back in because of that charge on the inside. So sure, initially when you make that leak, there's going to be what we call an efflux, a kind of a leaving of potassium ions as they leave because they follow the chemical gradient. But then they're also attracted back in by the electrical gradient. So there's a gradient charge, remember? There's positive out here, negative here. There's a gradient. Right? And so there are two gradients at play here. There is a chemical gradient that's having potassium leave our artificial cell, leaving our membrane here. And there's an electrical gradient trying to pull them back in. And there is a point where they're both balanced. There's an equal amount leaving, the equal amount coming back in for different reasons, whether it's electrical or chemical. And we call this the electrochemical equilibrium. The electrochemical equilibrium is defined by what we call an equilibrium potential. And so this equilibrium potential is telling us where is this balance point between the two gradients. And we measure what that balance point is by looking at the potential, the voltage difference of the inside of the cell versus the outside of the cell. We often call this the membrane potential because this is the difference across the cell membrane. Oftentimes we call this the membrane potential. And so